Okay, welcome back. This is Chapter 3. Chapter 3 and Chapter 4 are kind of important. You really need to understand the concepts here and understand them pretty well. If you don't understand what we're going to talk about here in Chapter 3, you're not going to understand what we talk about in 4. And if you don't understand what we talk about in 3 and 4, you're going to have a really hard time making it through the rest of this course. And if you somehow make it through the rest of this course, you're going to have a really hard time making it through General Chemistry 2. You've just got to know these. They're kind of critical chapters. So do the best you can, understand it as well as you can, rewind if you have to, ask questions. I'm around, so you can find me somehow. All right. So now that everybody is scared, let's go ahead and start Chapter 3. Okay, so if you'll remember, we talked a little bit about atomic mass, and we said that was a weighted average of all the isotopes of a particular element. And so the atomic mass kind of tells you how heavy an atom is. Right? Well, there are 92 naturally occurring elements in the universe. But there are somewhat on the order of, rough number here, probably pretty close to about 100 million different compounds out there. So wouldn't it be nice if I could take a concept that works for 92 different things and extend that to 100 million and 92 different things? Wouldn't that make me a whole lot smarter? Well, that's exactly what formula mass is. So formula mass is basically the weight of a molecule, just like atomic mass is kind of the weight of an atom. So formula mass is equal to the sum of the atomic masses in the formula. So let's say, for example, I had a water molecule, H2O. All right. Do I have H2O in my periodic table? Well, no, H2O is not in the periodic table. So how am I going to figure out how much a water molecule weighs? Well, think about it. Does this make sense to you? If I took 2 hydrogen atoms and an oxygen atom, and I put them on a scale, a little balance scale here, and I took a water molecule and I put it on this side over here, would they balance? Well, yeah, because, a water molecule is made up of 2 hydrogens and oxygens. So does it make sense to you? All I have to do is add up the weight of 2 hydrogens and 1 oxygen, and that's how much a water molecule might weigh. Well, you have just found something called the formula mass, and that's how you figure out the weight of a molecule. So, for example, what are the formula masses of H2O? And while we're at it, can you name this compound for me? Is it barium sulfur oxide? Is it barium sulfide? Is it barium sulfate? Is it barium 2 sulfate? What's barium sulfate? 8 is the oxygen, polyatomic ion with the oxygen. Group 2 metal, remember, always plus 2, so you don't have to use the Roman numeral, so just barium sulfate. Okay, well, can you find the formula mass for me? Well, let's start out with the water. Okay, so how do I figure out how much a water molecule weighs? Well, I look up the mass of a hydrogen, and if I look in my periodic table, I see that is 1.008. So there's 2 of them, so we're going to multiply that by 2. Then I look up the mass of an oxygen atom in the periodic table, and I find that is 16. So 2 times 1.008, 2.016, 2.016, plus 16, 2 places past the decimal, 18.02 AMU. All right, and that's how much a water molecule weighs. All right. Barium sulfate. Technically here, barium sulfate is found in a crystal structure. You don't find molecules of barium sulfate. It's an ionic compound. So technically what you're finding here is you're finding the formula mass of something called the formula unit. All right. The formula unit is the smallest piece of a crystal structure that you can take and just kind of repeat and generate the entire crystal structure. So it's kind of like tiles on a bathroom floor, you could say. All right, but mathematically, if you treat it as if it was a barium sulfate molecule, you still get the same answer. It's not going to cause any error. All right, so how would I figure out the formula mass of barium sulfate? Well, I look up barium in the periodic table, and that's 137.3. I've got a sulfur here, that's 32.07. And I've got 4 oxygen atoms, each at 16 apiece. So 4 times 16, that's 64, plus another 32.07, 137.3. Looks like one place past the decimal when I'm adding here, so we round that to 233.4 AMU. And that's how you figure out the formula mass. So formula mass is pretty simple. You just simply add up the atomic masses, in the periodic table. All right? And now what you can do is not only can you compare masses of atoms to atoms, now you can compare masses of atoms to molecules and even molecules to molecules. Find me an atom in the periodic table that weighs approximately the same as a water molecule. Well, fluorine looks like it's pretty close. Fluorine is somewhere around 19. And water is about 18. So a fluorine atom and a water molecule weigh about the same. A water molecule is about 18 times heavier than a hydrogen atom. See, and so yeah, you can compare masses of atoms to molecules now. So see, you've taken something that you could do to 92 different things, and you have now expanded that to 100,000,092 different things. So see how much smarter you are? Okay, can you do that? Okay. Well, how much does a carbon atom weigh? Well, 12.01 grams? No. 12.01 AMU, atomic mass units, right? Well, do I have a scale in the lab that weighs things in atomic mass units? Well, no. I have scales that weigh in grams. So how much does a carbon atom really weigh? How could I figure that out? Well, since the atomic masses of hydrogen, chlorine, and nickel are 1.008 AMU, 35.45 AMU, and 58.69 AMU respectively, it follows that 1.008 grams of hydrogen, 35.45 grams of chlorine, and 58.69 grams of nickel all contain the same number of atoms. And what that is right now, we're going to call it N sub A. All right? Now, stop for a second and think about this, why this has to be true. All right? Where did I get the 1.008, the 35.45, and the 58.69? Well, those are just the masses of the atoms in the periodic table, right? Okay. Why is this statement true? Well, let's pretend like you've got a 1 pound weight and you've got a 10 pound weight. How much more does my 10 pound weight weigh than my 1 pound weight? Well, 10 times heavier, right? Well, let's say I have 3 1 pound weights and 3 10 pound weights. My 3 1 pound weights weigh how many pounds? Well, 3 pounds. My 3 10 pound weights weigh how many pounds? Well, 30 pounds. How much heavier are my 10 pound weights than my 1 pound weights? Well, 30 divided by 3, they're 10 times heavier. Let's say I've got 7 1 pound weights. Well, that's 7 pounds. And I have 7 10 pound weights. Well, that's 70 pounds. How much heavier are my group of 10 pound weights than my 1 pound weights? Well, they're 70 divided by 7, they're 10 times heavier. Do you see, as long as I have the same number of 1 pound weights and 10 pound weights, my 10 pound weights are always going to be 10 times heavier because each individual 10 pound weight weighs 10 times as much as a 1 pound weight. Does that make sense? Stop if you have to and think about this. Okay? Well, I know that a chlorine atom weighs 35.45 AMU. And I know that a hydrogen atom weighs 1 AMU. So therefore, a chlorine atom is about 35 times heavier than a hydrogen atom. Make sense? So if I have 35 grams of chlorine and 1 gram, roughly, of hydrogen, those two quantities, since I've got 35 times the weight here, those two samples ought to have the same number of atoms. Now, we don't know how many that is at this point, but we know it's got to be the same. Just like if I have a group of 10 pound weights and a group of 1 pound weights, and if my group of 10 pound weights are 10 times heavier than my 1 pound weights, I know there's got to be the same number of weights there. hit pause and think about this if you have to. Okay? So therefore, what that means is I can take the atomic mass in the periodic table, I can take off the AMU, and I can slap a grams on there. And I take any element in the periodic table, and I put grams on the end of it there, on the atomic mass. All of those samples ought to contain the same number of atoms, and we're going to call it N sub A at this point. Well, do we know what that is? Well, it turns out we do. N sub A is something called Avogadro's number, and you don't want to see me derive it, and I don't want to show you. You're just going to have to take my word for it at this point. Avogadro's number happens to be equal to 6.022 times 10 to the 23rd, roughly. All right? So, therefore, 6.022 times 10 to the 23rd atoms of any element in the periodic table has a mass of whatever the atomic mass in the periodic table is, put a grams on the end of it. And so notice what you've done is you've just gone from AMU, which is something you can't measure in the laboratory, something relative, to grams, something you actually can measure in the laboratory. All right, so for example, what is the mass of one chlorine atom? Well, I know it's 35.45 AMU. Is it 35.45 grams? No. So how much does one atom of chlorine weigh? Well, what do I know here? Well, I know I've got one atom of chlorine. Remember all that factored label stuff I said was going to come back someday? Well, here we are. So I'm going to write that down. Okay? Then I ask myself, do I know a direct relationship between atoms of chlorine and grams of chlorine? Well, I know that 6.022 times 10 to the 23rd atoms of chlorine weigh how much? Well, 35.45 grams. Where did I get the 35.45 from? That's the atomic mass in the periodic table. See, take the atomic mass in the periodic table, slap a grams on the end of it. That's how much 6.022 times 10 to the 23rd atoms of that weigh. What do I put on top? What do I put on bottom? Well, I put the atoms on bottom. Why do I put the atoms on bottom? I want my atoms to cancel out. What am I left with? Grams of chlorine. So look what you've done. You've just figured out how many grams one atom of chlorine weighs. You don't have to use AMU anymore. You don't have to use these relative mass units. You can actually figure out how much it weighs in grams. So now we do the math. We got 1 times 35.45, which I think is 35.45, divided by 6.022 times 10 to the 23rd. How many significant figures here? 4. How many here? 4. So how many should my answer have? 4. Okay, so I run that through the calculator, and I get 5.887 times 10 to the negative 23rd grams. And that's how much a chlorine atom actually weighs. Or, if you want to put it in decimal form, it's this, 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 How far out do your scales in the lab go? They'll go out to 3 decimal places, right here. You ever have someone walk by and bump the table? And that little pen's jumping up and down, you can't get that digit to settle when you try to tear it? You have to close the glass case? Well, that happens when you're going out to the nearest thousandth of a gram. They make balances that go out to here. They go out to 4 decimal places. These are analytical balances. Any kind of air current at all on a 4-digit balance will throw it off. So you've got to close the door. I weighed something one time that actually absorbed water from the atmosphere. You had to weigh it quick because it got sticky. And you could actually literally watch that 4th digit climb as it was pulling in water from the atmosphere. That's how sensitive. They make balances that go out to 5 digits even. When you weigh things on a 5-digit balance, you have to wear gloves. Why do you have to wear gloves? Well, the oil from your fingerprint will actually throw off the mass in that 5th decimal place. How much further do we have to go to weigh that chlorine atom? Do you think you'd ever be able to make a mechanical balance that would weigh a chlorine atom? No, probably not. But can you calculate it? You can, because you know something about Avogadro's number. All right, we'll try another one. Okay. A nickel paperclip weighs 1.235 grams. How do I know that a nickel paperclip weighs that? Well, because I weighed one time. This is the extent I go to give you guys a nice set of notes here. How many atoms of nickel are in that paperclip? All right, well, what do we know? Well, we know we've got 1.235 grams of nickel, so we're going to write that down. Okay. Where am I trying to go to? I'm trying to go to nickel atoms. Do I know a direct relationship between grams of nickel and nickel atoms? Well, I know for every 6.022 times 10 to the 23rd atoms of nickel, how much do those weigh? Go to the periodic table, find nickel, look at the atomic mass. So we got what, 58.69? Put a grams on the end of it. 58.69 grams of nickel, 6.022 times 10 to the 23rd atoms of nickel. Got it? What goes on top, what goes on bottom? You want the grams on bottom because you want those to cancel. See, put these grams here. See, you want to cancel out what you don't want, and you want to be left with what you do. All right, and so that would be atoms of nickel is what we're looking for here. So that's where we are, and so I guess it's time to do the math. So we got 1.235 times 6.022 times 10 to the 23rd divided by 58.69. We're multiplying here, so 4 significant figures here, 4 here, 4 here, so my answer should have 4. 1.267 times 10 to the 22nd atoms of nickel, or about that many atoms of nickel. That's a lot of atoms. Moral of the story, atoms are really, really tiny. You probably knew that, before you took this course, but now you can tell me how tiny they are. Do you think you could ever count all the atoms of nickel in a paperclip? Probably not. I don't think so. Is 1.235 grams, is that a reasonable sample size that you're going to run into the lab? Yep, that's something you're going to run into the lab all the time. So notice that you can't necessarily count them all, but you can calculate it because you know something about Avogadro's number. See, what Avogadro's number allows you to do is it allows you to go from how many do I have to how much does it weigh? Or how much does it weigh to how many do I have? And that's kind of important. Because when you see a balanced equation and you see maybe, say for example, 2 hydrogen molecules plus 1 oxygen molecule goes to 2 water molecules. All right, that does not say 2 grams of hydrogen reacts with 1 gram of oxygen and produce 2 grams of water. What it says is 2 molecules of hydrogen react with 1 molecule of oxygen, produce 1 or 2 molecules of water. Molecules react with molecules. Grams don't react with grams. But the problem is, see, I can't count them. There's way too many of them. What can I do very easily? Well, I can put them on a scale and I can weigh them, see? And if I weigh them, then I can use Avogadro's number to tell me how many there are. So, it's a very powerful concept. Avogadro's number allows me to go from how many do I have to how much do they weigh? Or how much do they weigh to how many do I have? Because one I can measure very easily, but the other I need if I'm going to start doing some calculations and some things that are actually pretty useful. Okay? Do you get this? If you don't get this, you're not going to get what we talk about next. Everything kind of builds at this point, so try to wrap your head around it. Okay? Well, 1.267 times 10 to the 22nd atoms. 5.887 times 10 to the minus 23. Can you visualize that? Can you get that in your head? Can you imagine how big 1.267 times 10 to the 22nd is? Probably not. We don't do well with really large numbers. I like numbers like 3. You know, I can conceptualize 3. 3 is not a problem for me. But 1.267 times 10 to the 22nd, after a while, numbers just get big. And one number is just pretty much as big as the other. And it works in our brains the other way. You know, when numbers get tiny, they just get tiny. We can't conceptualize things. I like numbers like 3 and 13 and 0.5. Those are things that my brain can handle. All right. The problem is this is just how tiny atoms are. You know, wishing does not make it so. And so I guess I'm going to have to deal with some really large numbers. Well, what do we do when we have large amounts of things and we want to try to wrap our mind around it? Well, what we do is we come up with grouping numbers. Okay. For example, let's say I had a dozen donuts. How many donuts do I have? About 12, right? What if I had a dozen pencils? Well, that's 12 pencils. You know, what if I had a dozen paper clips? Well, that's 12 paper clips, because that's what a dozen means. It means 12 of anything, right? Okay. Well, here's something called the mole. All right, and a mole is not a furry little creature that digs holes in your lawn. A mole is something fundamentally different in chemistry. All right, a mole is really not even a thing at all. What it is it's a grouping number, kind of like a dozen. One mole, and this is how they abbreviate it, MOL. I know it's not much of an abbreviation, but that's just kind of what they do. One mole is equal to 6.022 times 10 to the 23rd of anything. Hey, there's that number again, Avogadro's number. All right. So if I have a dozen donuts, how many donuts do I have? Well, I have 12. What if I had a mole of donuts? Well, I have 6.022 times 10 to the 23rd donuts. I have a lot of donuts. All right, so a mole is really not even a thing. It's a grouping number. All right, why do I need such a large grouping number? Well, because look how many atoms we've got in this nickel paper clip up here. That's a lot, right? What I need is a large number to bring things back down to size. All right, so I can deal with smaller numbers. Okay, well, why not like a trillion or a billion or even 1 times 10 to the 23rd? Seems like that would be simpler to use. Why am I using such a weird number like 6.022 times 10 to the 23rd? Well, it actually makes your life easier to use that number. How so? Well, 1 mole of hydrogen atoms is equal to 6.022 times 10 to the 23rd atoms of hydrogen. That's the definition of a mole. How much do those hydrogen atoms weigh? 1.008 grams. Where did I get the 1.008 grams? That's the weight of hydrogen in the periodic table. See, you'll always have a periodic table on a test. 1 mole of chlorine atoms is equal to how many chlorine atoms? Well, 6.022 times 10 to the 23rd atoms of chlorine. How much do they weigh? Well, 35.45 grams, atomic mass according to the periodic table. All right, now watch my change in terminology here. The way you find chlorine is you don't find it as chlorine atoms, but you find it as Cl2 molecules. How many Cl2 molecules do I have in 1 mole of chlorine? Well, 6.022 times 10 to the 23rd molecules of chlorine. See, that's the definition of a mole right there. How much do they weigh? 70.90 grams. Where did I get the 70.90 grams? Well, in 1 molecule of Cl2, there are 2 chlorine atoms. How much does each chlorine weigh? Well, it weighs 35.45. See? So 35.45 times 2, 70.90 grams. I found the formula mass. See, if you don't know how to do formula mass, you can't do this. Got to be able to do that before you can do this. Everything builds in this chapter. All right? Now, notice I didn't ask you in that second example, third example here, how many chlorine atoms are there. I said, how many of those little Cl2 molecules are there? So Cl2, 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 Cl2. And there's this many. Well, in that sample, notice there's twice as many chlorine atoms as in this sample. So shouldn't it weigh twice as much? It should if there's twice as many atoms. So see, I may be confusing, but at least I'm consistent. You know, this stuff does make sense, or at least it is consistent. I won't necessarily say it makes sense to you at this point, but at least you have a fighting chance of learning this. You just have to sit there and concentrate. All right. How about a mole of HCl molecules? Okay, this is hydrogen chloride, by the way. In a water solution, this would be hydrochloric acid. Yeah, watch the last video. Okay, but as hydrogen chloride molecules, 1 mole of HCl is equal to how many molecules of HCl? 6.022 times 10 to the 23rd. Definition of a mole. How much does it weigh? 36.46 grams. Where did I get the 36.46 from? Well, I took the mass of a hydrogen and a chlorine and I added them together and I got 36.46. I found the formula mass. All right. So 1 mole of anything is equal to its atomic mass in the periodic table if it's an atom, or its formula mass if it happens to be a molecule, slap a grams on the end of it, and that's how much it weighs. And moles tell me how many do I have. Okay, and it's a grouping number. It brings the numbers down to size so I don't have to deal with big, giant, huge numbers like this one up here anymore. Okay, this tells me how many. This tells me how much it weighs. And so that allows me to weigh things in the lab, correlate that back to here. Or I could do this and predict how much would it weigh. Very powerful concept, if you think about it. Got it? Okay. Well, let's talk a little bit about molar mass. Generalizing from the above examples, the molar mass, and that's molar mass, is numerically equal to the formula mass. Okay, this is one of those things, if you take a physics class, you talk about mass versus weight, and we pretty much use those terms interchangeably, in the real world, but, there's always some physics major out there. I was a physics major, by the way. Well, really, technically, weight is a force, and mass is actually mass, and you just kind of want to slap them. But most of the time, we pretty much use the terms interchangeably, even though technically they're not exactly the same. All right. Well, this is kind of the same thing. Molar mass and formula mass are similar. Technically, there's a difference. Does it matter 99% of the time? Not really. So I'm going to mention this, and then after that, we will never speak of this again. All right? Okay. So let's say, for example, I've got CaCl2, so that's calcium chloride, not calcium dichloride. Refer back to naming compounds. Calcium chloride. What is the formula mass? Well, we take the weight of a calcium here, which is about 40.008. I don't have my periodic table with me, I'm guessing here. 2 chlorines at 35.45 apiece, so 70.90 and 40.00A, about 110.98, I think is what I came up with there. 110.98 AMU. Okay, so that's the formula mass. What is the molar mass? Well, molar mass, how much does 1 mole weigh? Or its mass, I guess. 110.98 grams per mole. And that's molar mass. Okay? Notice they're pretty much the same thing, it's just the units. This is a relative mass, this formula mass. This is an actual or an absolute mass. It's 110.98 grams per mole. And that's really the only difference. Okay? C6H6O6, this is glucose. Okay? Simple sugar. Your body can actually use this, not table sugar, that's sucrose. But your body, this is what they feed you in an IV. They don't grind up a Big Mac and put it in there. But yeah, this is your body can use this straight. Doesn't have to digest it or anything like that. How much does it weigh? Well, I've got 6 carbons here at about 12.01 apiece, and 12 hydrogens here at 1.008. Okay, and then 6 oxygens here at about 16. So 6 times 16, that's what, 96, and 12.12 roughly, and 6 times 12 is what, 72. Add all that together, and you get somewhere in the order of 180.18. You can check me if you'd like. All right, in fact, you probably should. Just get used to calculating formula masses. 180.18 AMU. All right, and that's the formula mass. What's the molar mass? Well, it's 180.18 grams per mole. 1 mole weighs 180.18 grams. See? So, just like mass and weight, are they different? Yeah, technically they're different. Does it really matter? Probably not most of the time. We're going to use the terms formula mass and molar mass pretty much interchangeably in here, just like people sometimes use weight and mass the same. So yeah, we'll probably won't talk about this again. All right, well, let's move on to something else then. Okay, this is an important skill. If you can't do this, you are dead in the water in here. You know, you've got to be able to do this. This is a big one. So make sure that you can do this. Okay, and that's mole mass conversions. All right, how do I go from moles to grams, grams to moles? All right, so for example, calculate the mass in grams of 13.2 moles of calcium chloride. Okay, well, what do I know? I know I've got what? 13.2 moles of calcium chloride. So we're going to write that down. Draw a time sign, make a factor over here. Okay, where am I trying to go? I'm trying to go to grams, mass in grams, so grams of calcium chloride. So I asked myself, do I know a direct relationship between grams of calcium chloride and moles of calcium chloride? Well, I know that 1 mole of calcium chloride weighs how many grams? 110.98 grams. Where did I get the 110.98? That's the formula mass of calcium chloride. Took the weight of the calcium and 2 chlorines, just like I did on that previous page. Put a grams on the end of it. That's all we did. See, if you can't do formula mass, you can't do this problem. You can't do this problem, by the way, you're dead in the water with what we're going to do the rest of the chapter. Got to be able to do this. This is important. Okay? What goes on top, what goes on bottom? Well, you want the moles on the bottom. Why do I want the moles on the bottom? Because I want to cancel these moles, and I want to be left with grams. See? So now I've got grams. So now we do the math. 13.2 times 110.98 divided by 1. This is exactly 1. I'm multiplying, dividing. How many significant figures here? 3. How many here? 5. How many should my answer have? 3. So 1.47 times 10 to the 3rd grams of calcium chloride, or 1,470. I would take either one. All right? Calculate the number of moles in 16.4 grams of glucose. All right, what do I know? I know I've got 16.4 grams of glucose. Where am I trying to go to? I'm trying to go to moles of glucose. Do I know a direct relationship between the two? Well, I know for every 1 mole of glucose, that weighs 180.18 grams. Where did I get the 180.18 grams? Well, it's just the formula mass. See, you got to be able to do formula mass, because if you can't do that, you can't do this. If you can't do this, you're going to have a really hard time doing what we're going to talk about next. All right? Okay, so we cancel out the grams here. We're left with moles of glucose. 16.4 times 1 divided by 180.18. 3 significant figures here, 5 here, so my answer should have 3. So that would be 0.0910 moles of glucose. 1, 2, 3. Zeros preceding non-zero digits are not significant. Zeros after non-zero digits after the decimal are. So that counts, that counts, that counts. And there you go. All right, can you do that? Kind of a big deal. You need to be able to go from moles to grams, grams to moles. That's going to be very useful to you in this chapter and also the next. So practice. Practice that factor label system. I told you it was going to come back, and I told you it was going to be useful. Well, here it is. All right, hope you learned it. All right. Okay, well, if you have to go over it again, rewind and listen. You can always email me if you have problems. The concept of a mole sometimes, if you've never seen this before, is a little fuzzy. Sorry. But you get used to it after a while. Once you stop thinking of a mole as a thing, it gets a little bit easier. So look at that. We'll apply all that in the next video. We'll talk about simplest formulas and molecular formulas again, if you'll remember. We talked about those briefly, and we'll go from there in Chapter 3. So that seems like a fairly decent place to stop. So we'll quit right there, and we'll see you next time. Bye.